Welcome to Lecture 1.1. In this lecture, I'll be introducing NMR, or nuclear magnetic resonance, a very powerful technology and a technique that allows us to determine the structure of an unknown chemical. We can do this by focusing on specific atomic nuclei. But first, let's really visit this question of what chemical do I have? When practicing organic chemistry, you may be trying to reproduce a previous synthesis that someone else has done, or you're trying to maybe do some novel chemistry. You're trying to make a new chemical. In both cases, you're going to prepare some sort of reaction, you're going to let it progress. And we've learned previous tools, like maybe infrared spectroscopy or TLC, that can help us get some information about our chemical. But at no point were we 100% confident that what we had was the chemical we expected. Nuclear magnetic resonance really allows us to answer that question with a lot more certainty by providing us very detailed structural information that will allow us, from a spectra and a chemical formula alone, to develop and be very confident about the full structure of an unknown chemical. In order to use NMR, again, we need to focus on specific atomic nuclei. Those nuclei must have an odd number of protons and neutrons. Let's discuss some common atoms we're going to be seeing. So first, let's talk about the humble proton, or the hydrogen. Now, hydrogen in its 1H form, or that isotope, is NMR active. It exists in 99% abundance, which means that the 1H isotope of hydrogen is the most common by far, and this makes it a great NMR target. However, deuterium, also sometimes called 2H, is an isotope of hydrogen, has an extra neutron. So deuterium is not NMR active. It's also at low abundance. Now, the reason that it's not NMR active is that it has an even number of protons and neutrons. The full mechanics of that I'm not going to get into in this course, as I'm here to cover the core ideas and help you understand the use of NMR. Both of these things together make this a poor NMR target. Now, looking at carbon, carbon is a little different. It may appeal to us as it's a very common isotope. Right? Carbon is everywhere in organic chemicals, and if we could use it, that would be great. The problem is, carbon-12 has an even number of protons and neutrons and is not NMR active. This makes it a very poor NMR target. It's not going to work. However, 1% abundant is carbon-13, or the heavier isotope of carbon, which is used for carbon radio dating, and it is NMR active. Awesome. This makes it a good NMR target, but its low abundance can be a problem. Now, in this course, I'm going to focus entirely on 1H NMR, as it's by and large the most useful tool, and one that most universities will focus on entirely. Some universities may focus with their curriculum on carbon NMR, and that won't be covered here in this course. A lot of the principles are similar, but 1H NMR is more difficult and more informative. So basically, by understanding everything we can about the hydrogen in a molecule, we're able to elucidate its full structure. Let's quickly take a second to look at IR and how it compares to 1H, or hydrogen NMR. Imagine you were given a chemical formula of C4H8 and an IR spectra. As a reminder, an IR spectra provides information about the kinds of bonds present in a molecule. Here, we see peaks representing sp2 carbon-hydrogen stretches, as well as a signal that's relatively informative as a carbon-carbon double bond stretch. Given that this molecule has 1 degree of unsaturation, which could be a double bond or a ring, this provides us with fairly strong evidence that our molecule possesses an alkene. Now, given that it's a very small molecule, we only have a few options, and there are 4 isomers here. The problem is that IR, at least based on these characteristic peaks, won't really help us tell these 4 apart. Any 4 of these molecules would be expected to have similar peaks in this region. Now, the fingerprint region may be slightly different, but that was something more for computers, something that we don't really deal with as chemists. Now, what does 1H NMR look like? Right? Clearly, IR is helpful, but it's not giving us the full picture with confidence. If I'm taking a drug, I don't want it to be one of these 4. I want to know what it is. So the 1H NMR spectra looks something like this. It's a little bit different, and we'll break it down in a lot more detail, so don't worry if you're confused looking at this right away. You'll notice that there isn't a y-axis, there's only an x one. And there are some weird peaks coming off of that x-axis. Now, using the NMR spectra, we can virtually guarantee that this is the isomer that we're talking about. The other three would not look this way on 1H NMR. And after we get through all the material, maybe you can come back to this and try to understand if that makes sense. Now, clearly we're going to need to do a lot of coverage first before we can come back to answer that question. But we care about NMR because it gives us this concrete information. So let's talk about the overall picture of solving structures using NMR. Here is a representative NMR sample that I'll be coming back to over and over. I want to first mention this idea of signals. So I've labeled them here as A, B, and C, these signals that are coming off of the x-axis with a lot of different bells and whistles. Each signal represents an equivalent group of hydrogens. Now, we're going to define this in the next session, or the next lecture. But importantly, I want to talk about the three pieces of information that each signal gives us. First is the location of that signal along that x-axis. We call this the chemical shift of the signal. Briefly, this gives us information about what is around the hydrogen. Right? Is it connected to electronegative atoms like oxygen? Is it connected to something like a benzene? We don't get perfect information with chemical shift, but it gives us some idea about what is around these hydrogens. One piece of the puzzle for each signal, clearly not enough to be very confident. The second piece of information that each signal gives us is the integration. As you can see, the chemical shift is beneath the x-axis, and sometimes the integration is given in different ways, but typically I've seen it given as a number beside an integral. Now, integration, this number that each signal will have, represents the number of hydrogens represented by a signal. As I mentioned previously, each signal represents a group of hydrogens, which could be 1 or 2 or 3 or even more. We'll discuss what makes these hydrogens group up like this in the next session. But for now, the number of hydrogens represented by a signal is given to us by that integration piece. The final piece of information, and sometimes more notoriously difficult, is understanding the multiplicity of the signals. Really, this is the shape of the signal, sometimes conflated with the number of peaks. While similar, the shape is really important, as we'll discuss. But the shape of the signal, for example, you can see that signal A, if I zoom in, has 1 peak. Signal B has 4 peaks, but they're not 4 peaks like this, of equal height. There's a specific pattern where they seem to be symmetric down the middle, increasing in intensity into the middle and then decreasing afterwards. We see the same thing with C, except it has 3 peaks. We'll definitely dive into the very crucial information that the shape of the signal gives us. But for now, this helps us understand the number of nearby hydrogens for that given signal. So clearly, compared to IR, there's a lot more going on here with 1H NMR. How are we going to use it? One way, and I'd like to mention this before we go into the big detail, is just to help you understand where we're going with this. Given an NMR spectrum, I like to always make a table. The table will have the signals labeled however you want to label them. I like to do from left to right. And then we'll have a section for chemical shift. In this case, signal A, which is this signal here, has a chemical shift of 4. Signal B has a chemical shift of 3.5. And signal C has a chemical shift of 1.7. The integrations are 1, 2, and 3. And we can list the multiplicities as well. Again, we're not doing a full NMR spectrum here. The idea is that the information given to us in the spectrum can be neatly organized in a table format. And once we have that table filled out, and once we understand what those pieces mean, we really don't need the spectrum anymore. We have that information, and from that table alone, as well as, of course, the chemical formula, we'll be able to deduce the structure. So that's the introduction to NMR. In our next lecture, I'm going to focus on what the signals are in NMR and what it means to be an equivalent group of hydrogens. I'll see you there.